Hello everyone. Today we're going to look at various parts of functions. So first we're going to define what a function is. A function is a type of relation that assigns exactly one output for every input. So this means that one x value will have exactly one y value. So if we look here at this particular box, we have set A and set B. Let's say that set A are our x values and set B are the y values. If I asked you to tell me what the domain is, the domain represents the set of all of your x values. So you would look at this graph or chart here and you would say that our domain consists of the numbers 1, 2, 3, and 4. If I asked you for the range would be the set of all of the y values. Now notice here on this box that all of the x's, they're leading to these y values, and 7 is not used. Therefore 7 would not be included in the range. Our range would then just be 6, 8, and 9. So now we're going to look at what determines a function, and we should be able to look at different kinds of relationships and see, yes, it is a function, or no, it's not a function. Graphically, since x's in a function do not repeat, this means that I can draw a vertical line across the function, and it would only cross exactly one time. This is called the vertical line test. If your graph passes the vertical line test, then it is a function. Versus we look at this graph here, we see that this vertical line crosses twice. This means that if I were to write down the coordinates, let's say for example, this one here would be -1, 1.75, and this one would be -1, -1.75. You'll notice that these x's here repeat. Therefore, this is not a function. In this example here, what we're going to do is we're going to look at these various representations of relationships, and we have to determine whether or not it is a function. For A and B, we have verbal descriptions. Remember that when we're given a relationship, a function is when the x's do not repeat. The y's can repeat, but the x's definitely can't. So what we're going to focus in on are the input values. So for this one, it says that the input value of x is a student's ID number, and the output value y is that student's score on a physics exam. It doesn't matter if multiple students have the same score on the physics exam because that is the output value. But the input value represents an ID number, and ID numbers never repeat. So this would be considered a function. For B, it says the input value of x is the area code, and the output value y is a phone number in that area code. Since area codes are the input, and area codes do repeat, then this would be considered not a function. For this chart here, charts and graphs are easier to determine if they're functions because we're just going to look at the x values. And we see here that these x values repeat. Therefore, C is not a function. For D, if I were to draw a vertical line, we see that we pass through these 2 points. And since it's passing through 2 points, D is not a function because it fails that vertical line test. With equations, if you're trying to figure out whether this is considered a function or not, I wrote here that we could solve for y. If it yields only one answer, then it is a function. So for example, in E, we have y squared minus 2x is equal to 5. Let's solve for y. I would first add the 2x over, and we would get that y squared is equal to 5 plus 2x. Then to get the y alone, we would have to square root both sides. making y equal to plus or minus the square root of 5 plus 2x. Remember, when we square root anything, it is always plus or minus. So this means that if I were to plug in an x value, I would get two y values for that same x, meaning that that particular x value would repeat. So this would be not a function. Now the shortcut for this is that we're going to focus on the y value when we have equations. If the y value has an even exponent, then it is not a function. And that's because if it's an even exponent, we would have to get the square root or the fourth root or the sixth root, whatever root, and it would always be plus or minus, giving us two y values for the same x. So that's a shortcut. So if I look at f here, I don't necessarily have to solve for y. I look at the exponent for y. Since it doesn't have one, that means the exponent is 1. And 1 is an odd number, making f a function. We're going to continue now with finding function values. Now in this class we use exclusively function notation, which is where we use f of x instead of y, or g of x or h of x, whatever letter of x. That represents the y value. So if I wanted to find g of 6 in this example, this means that we're looking for the y value when x is equal to 6. So if we want to solve, what we would have to do is plug in 6 into every x value. So that would mean that we would have 6 squared plus 8 times 6 minus 24. And then we work it out. 6 squared is 36 plus 8 times 6, which is 48, minus 24. When you add all of this together, or you combine, you would end up with the answer of 60. Moving on to g of negative 4x, this means that for every x value that is in my function, I am going to substitute it with negative 4x. This means that our actual answer is not going to be a number like in a, but it's going to be another expression. So here we go. So we would do negative 4x squared plus 8 times negative 4x minus 24. Since this is squared, we have to remember that when something is getting squared, that means that it is that term times itself. So we would do negative 4x times negative 4x, and then 8 times negative 4x, and then minus 24. Negative 4x times negative 4x is a positive 16x squared. 8 times negative 4x is negative 32x, and then minus 24. Since none of these are like terms, this would be my answer. Now for this one, I am plugging in a binomial. A binomial is when you have two terms. So you'll have a term and then plus or minus another term. So we're looking for here g of 5c plus 4. So for every x value, I am going to plug in 5c plus 4. So we have 5c plus 4 squared plus 8 times 5c plus 4 minus 24. Now when you have a binomial that is getting squared, that means that we have 5c plus 4 times itself, 5c plus 4. Meaning that we are going to have to FOIL. And remember that FOILing just means that we take every term from the first binomial and distribute it to every term in the second binomial. So what we would do is we would do 5c times 5c, and then 5c times 4, then 4 times 5c, and then 4 times 4. So this would give us 25c squared. Then plus 20c, then plus another 20c, and finally plus 16. Moving along with the rest of my expression, I'm going to distribute this 8, and that would give me plus 40c plus 32, and finally that minus 24. Once you have everything distributed, we can go ahead and combine like terms. We always want to make sure that our answer is written in standard form, meaning that we start with the highest exponent and work our way down. So our first term would be the 25c squared. Now I like to cross out terms as I use it, so that way I can focus on what's left. Next, we're going to combine all of our c's. We have 20c plus 20c plus 40c, which gives me positive 80c. And then finally, we have our constants left. We have 16 plus 32 minus 24, which gives us a positive 24. And this would be our answer. We're going to do one more just to make sure that we understand how to find these function values. So for f of 3, we're going to plug in 3 into every x of f of x, which is x squared minus 2x minus 8. So we're going to go ahead and plug that in. We would get 3 squared minus 2 times 3 minus 8. 3 squared is 9, minus 6 minus 8. 9 minus 6 is 3, and 3 minus 8 is negative 5. So this would be our answer. For f of negative 3d, we're going to plug in that negative 3d inside of every x, giving us negative 3d squared minus 2 times negative 3d minus 8. Remember that negative 3d squared means negative 3d times negative 3d. If you have a monomial, meaning one term that is getting squared, you can simply apply that exponent to every term. So this would give me a positive 9d squared plus 6d minus 8. See, it's already in standard form. There's nothing left to combine, so this would be my answer. With this final one, we're going to go ahead and plug in that binomial. This means that once I plug it in and it's getting squared, I will have to FOIL. So we have this 2a minus 1 squared, which means that we have 2a minus 1 times 2a minus 1. And then, of course, the minus 2 times 2a minus 1, and then minus 8. So now I'm going to go ahead and FOIL. 2a times 2a is 4a squared, and 2a minus 1 is negative 2a. Then I go ahead and distribute this negative 1. So I have another negative 2a, and then plus 1. Then over here, I can go ahead and distribute that negative 2. Negative 2 times 2a is a negative 4a. And negative 2 times negative 1 is a positive 2. And then, of course, the minus 8. Now that everything is distributed, we are free to combine like terms. Our first term is the one with the highest exponent, so 4a squared. Then we have negative 2a minus 2a minus 4a, which gives me a negative 8a. Finally, we have this 1 plus 2 minus 8, which gives us a negative 5. And this would be my final answer. Moving along with functions, we are going to need to be able to determine the domain. But before we do that, I got ahead of myself. We are going to use this piecewise function to evaluate for these function values. Now, when we're evaluating for function values using a piecewise function, we have to pay attention to the pieces. A piecewise function is exactly what it sounds like. It is a function that is divided into different pieces. So you'll see here that this first piece, that 4t, we only use it if the t value that we're using is somewhere between 0 and 15. For the second piece, we have that it's 60, and the answer will only be 60 if t is between 15 and 240. And finally, with the last piece, we have this last equation, and we only use that equation if the t value is between 240 and 250. Now this function is represented by this verbal description here. We have the speed v of a vehicle in miles per hour can be represented by the following piecewise function when t is the time in seconds. Find the speed of the vehicle at each indicated time. So, keep in mind, like if you're out driving or you're in a car, you're not going at the same speed the entire time. You may sit in traffic, you may get on the highway, and these all entail different speeds. That's why this particular function is broken up in pieces, because from 0 to 15 seconds, your speed can be determined by 4 times t. Between 15 and 240 seconds, this means that the speed is a constant 60 miles per hour. And then from 240 to 250 seconds, we can determine our speed by just plugging in the number into this equation. So if I'm trying to look for v of 10, v of 10 is between 0 and 15. So I would plug in the 10 into that first piece. So v of 10 is going to equal to 4 times 10, which is equal to 40. And this is miles per hour because the v value represents the speed in miles per hour. For v of 30, 30 is between 15 and 240. So we don't even have to solve anything. V of 30 is automatically 60 miles per hour because the car is traveling at a constant speed at that time. For v of 240, we get that 240 is between 240 and 250, obviously, but then we also see the 240 right here. So how do I know which one I plug it into or which one of these pieces I'm going to use? Well, we can see here that t is between 15 and 240, but it does not include 240 because t does not equal to 240. However, in this bottom piece, where t is between 240 and 250, t also equals to 240. So this is where I would plug in the 240. So we would do negative 6 times 240 plus 1500. Negative 6 times 240 is negative 1440. And then I add it to the 1500, and that gives me 60 miles per hour. Now we're going to go ahead and review how to find domain and range of a function. When we are writing the domain and range, we are going to be using exclusively interval notation. Now in Algebra 2, we use both set and interval notation. Set notation includes inequalities. And then what we do is we're going to use inequalities to then translate to interval notation. Now, even though we are not going to be using set notation, we still use inequalities to help us find domain. So therefore, it's important to know how to translate inequality into interval notation. Now, an inequality tells us the start and end of a particular interval, with x being somewhere in between, or whether x is less than or greater than a particular value. When x is less than or greater than, those values are not included. And if it's not included, if it's not included, then we would use parentheses. If it is included, then we would use brackets. It's important to note as well that infinities are never going to be included. Included values have to be coordinates or points. Now with infinity, you can't put a point on infinity. You can't stop it, so therefore we can never include infinity. So first we're going to take a look at these inequalities that are in terms of x. So we'll say these are domains. And we're going to see how we can translate these domains to interval notation. Now, I'm a visual learner, so I like to be able to see what those inequalities represent. So I have here number lines, or just lines that we're going to turn to number lines to help us translate. Now, you don't necessarily have to always use a number line, but it is helpful if you have a hard time seeing what the domain would be. So for this first one, we have that x is less than 11. So what I do is I'm going to put 11 on my number line. Since it is less than and not less than or equal to, that means the 11 is not included. Since x is less than 11, that means that I would shade the left side of this number line. Keep in mind that on the left side of the number line is negative infinity, because the further left you go on the x-axis, the more negative those numbers become. So our domain here would be from negative infinity to 11, and we're using parentheses for both since neither are included. When we're writing our interval notation, we can use this number line as we read it from left to right, and it's those shaded areas. For this next inequality, we have the numbers negative 8 and 16. So I'm going to go ahead and put both on my number line. As we can see from the inequality, the negative 8 is not included, but the 16 is included. Now, when you see an inequality written this way, x is somewhere in between negative 8 and 16, since x is greater than negative 8, which is the right side of negative 8, and x is less than 16, which is the left side of 16. So when you see inequalities written this way, it's exactly what it looks like. The x is the shaded region in the middle. So therefore, the domain of this function would be parentheses, negative 8, comma, 16, and then a bracket, since that 16 is included. For C, we have x is greater than 9 or x is less than negative 2. So I'm going to go ahead and put those numbers on my number line. Always make sure that they are in order from least to greatest. Neither number is included, so I'm going to use open circles. For this first inequality, x is greater than 9, so I would shade the right side. And for this second inequality, x is less than negative 2, so I would shade the left side. Since we have two shaded regions, that means that the domain is going to have two intervals, two sections. So remember, the left side here is negative infinity, and the right side here is positive infinity. So for this particular inequalities, our domain would be from negative infinity to negative 2. I have to stop there because we have this empty section in the middle. Now, in order to connect this interval to my next one, we're going to use U, which means the union between this interval and that interval. So the domain would be this section as well as the second section, which is from 9 to infinity. For the next inequality, we have x is greater than or equal to negative 3. So I'm going to put negative 3 on my number line. The negative 3 is included, and since x is greater than, I'm going to shade everything that's to the right of negative 3. Our domain would then be bracket, negative 3, comma, infinity, and then parentheses. For E, E is similar to B. We're going to put both numbers on the number line, negative 4 and negative 1. The negative 4 is included, the negative 1 is not. And you see that x is in the middle, so that's that middle section here. So our domain would be bracket, negative 4 to negative 1, parentheses. F is very similar to C. I'm going to put both of those numbers on my number line. The negative 16 is included, where the 5 is not included. Here it says x is less than or equal to negative 16. So that's everything to the left of negative 16. X is greater than 5, so I'm going to shade the right side. So when we write the domain, it would be from negative infinity to negative 16, bracket, union, parentheses, 5 to infinity, close parentheses. Now we're going to actually take a look at some graphs. Keep in mind that the domain represents all of the x values of our function that are included. So we read our graph from left to right in order to determine the domain. The range, however, is a set of all of the y values of your graph. And we always want to write our intervals from smallest value to the greatest value. So I'm going to read my graph from the bottom up in order to determine the range. So when we look here at this particular graph, for the domain, I'm going to look at the very smallest x value on my graph, which just so happens to be x is equal to 0. Since the function actually touches that coordinate, that means that we're going to include the 0. And then it opens forever to the right, and towards the right is positive infinity. So we will close it with a parenthesis. Now for the range, the smallest y value on my graph is also 0, since this is the coordinate 0, 0. So I'm going to use a bracket for 0 for my range, and it does open up forever, so it goes towards infinity, and close parentheses. Now in this particular graph here, we have this, which is called a hole. A hole is exactly what it sounds like on a graph. It is an undefined value in your function. So for this particular function, we see that it goes off the graphs in either direction. So that means that for this function, the domain and the range would be all real numbers except for this hole here. This hole means that there is nothing there, and that is the coordinate 0, 1. Now I'm writing this down to show you that this x value will need to be excluded from the domain since it is undefined, and this y value would need to be excluded from the range since it's undefined. So when I'm writing my domain, we see that it's opening left forever, so I'm going to start to negative infinity. As we go along the graph, all of these x values here are defined except for this one. So I'm going to stop at 0, and I'm going to put a parenthesis to indicate that I am not including that value. However, there is more to the right of the graph, and it starts again from that hole. So I'm going to put a u, another parenthesis, and 0, because I'm starting at 0 again. And remember, the 0 is not included, so I'm using parentheses. Then it continues opening to the right forever, so it goes to infinity. The range is going to look very similar, except we are going to exclude that 1. We can see that this graph is going down forever, so therefore those are my negative y values, so we start at negative infinity. All of these y values are included except for this y value of 1. But, however, I see that it is included over here. So even though it is not included in the in this hole, that y value of 1 is included right here. Therefore, I don't need to stop there, and it does continue up forever, so I'm going to put infinity. Moving along, we're going to look at some additional graphs here. For the domain, for this quadratic function, this is a quadratic since it is a parabola. All quadratics open forever to the left and open forever to the right. Therefore, the domain is going to be from negative infinity to infinity. Now for the range, I'm going to look at the graph from the bottom up. I see that my very smallest y value is here at negative 1. It is touching that negative 1, so I'm going to use a bracket, start at negative 1, and then it goes up to infinity. Looking at this graph, I see that I have these two red dashed lines. These are asymptotes. And asymptotes are lines that your function will never touch. This vertical asymptote has the equation x is equal to 2. Remember, all vertical lines have the equation x equals. And this horizontal line is the equation y is equal to 3. So our function here, you can see, is split into two parts. And that's because these asymptotes break up that graph. The function is going to get infinitely close to the asymptote, but it will never ever touch. So when I'm finding the domain is affected by that vertical asymptote. since that is an x value. At x is equal to 0, there is nothing there. It is undefined. Therefore, I have to exclude this x value. For the range is going to get affected by the horizontal asymptote, which is y is equal to 3. So for my graph, the range would be all numbers except for this y is equal to 3. So when I write out my domain, it would be from negative infinity to 2, because there's nothing there because of that asymptote. And then I'm going to start again at 2. And it does open forever to the right, so infinity. Notice that I use parentheses for the 2's because I am not including those values. For the range is very similar. We're going to start with negative infinity because it does open down forever. But I have to stop at the asymptote, which is 3. And remember, we are not including that. But there's more above that line, so I would use a U and start again at 3. And then it goes up forever to infinity. Again, the 3 is not included because it is an asymptote and nothing is there. Now we're going to examine how to find a domain and range when we don't have a graph. So we don't have that visual cue. But instead, you're going to have an equation. Now, when you have a function's equation, if it does not have a radical and if it is not rational, meaning a fraction, then the domain is negative infinity to infinity because it is a polynomial type function. And all polynomial type functions have a domain of negative infinity to infinity. Remember, domain are your x values. And if you have a polynomial just means that you have multiple terms with exponents that are added together, such as, let's say, 3x to the third plus 4x squared minus 2x plus 1. Something like that would be considered a polynomial. And the domain would be negative infinity to infinity because I can plug in any x value that I want and I would get a y value. However, when you have a radical function is anything that has the square root symbol. Okay, with the square root, the one thing that I cannot have on the equation is a negative inside of that radical. Remember that a square root means that you're looking for two identical numbers that would multiply to give you what's inside. So let's say if I were trying to find the square root of negative 4, the only two numbers that would multiply to give me negative 4 would be either negative 2 and 2, negative 1 and 4, or 4 and negative 1. Obviously, these are not identical. And then for the negative 2 and 2, you're going to have one number that is negative, making it not identical. Therefore, whenever you have a negative inside of a square root, we always end up with I, which is an imaginary number. So you cannot graph that. Bottom line, you cannot have a negative inside of a radical. So when we're trying to determine the domain of a radical function, we take whatever is inside of it and we're going to make it greater than or equal to 0. That way it's excluding all of those negatives. As you can see on the graph, this is your graph of a radical function. And you see that here at 0 is defined, but there's nothing to the left of it because negatives are not allowed inside that radical. Now for rational functions are fractions. And the one rule for fractions is that you can never have 0 in the denominator. Remember that fractions are parts of a whole, where the numerator represents the part and the denominator represents the whole. You cannot have 0 as a whole. There's no way that you can have something out of nothing. So therefore, when we're trying to find the domain of a rational function, it's a lot easier to figure out the numbers that we would exclude than the numbers that we would include. And we do that by taking the denominator and making it not equal to 0, which means that the denominator cannot equal to 0, and solving for those x values would give me those excluded values. So here we have some examples of radical and rational functions so that we can find their domains. And in the blue boxes, you'll see how I applied the rule for each one in order to find that domain. For a, we have the square root of 4x minus 1. Since this is a radical function, that means that I have to take whatever is inside of that radical and make it greater than or equal to 0. Once I have that inequality set up, then I would use the inequality to solve for x. So in this case, I would add 1 first, and we would have 4x is greater than or equal to 1. Then I would divide the 4. And when I divide the 4, I get x is greater than or equal to 1 over 4. This is my domain. And what I can do here is what we did before. We can put it on a number line with 1 over 4 as our number. It is an included value. X is greater than, so it's everything to the right. So my domain is going to be bracket 1 over 4 to infinity. For b is a rational function because it is a fraction. Now when you have a rational function, remember you have to take the denominator and make it equal or make it not equal to 0 so we can figure out those excluded x values. So that's what I did. I have here in the box x squared minus 1 cannot equal to 0. And now we're going to use this equation to solve for x. Now keep in mind there are two ways you can solve this equation. You can just isolate the x variable, or you can factor since this is a difference of squares. For now, I'm just going to solve for x. So I'm going to add the 1 over to the other side, and we get so far that x squared is equal to 1. And then I would square root. When you square root, you get x is equal to plus or minus 1. Remember, when you square root anything, your answer is always plus or minus. This means that x cannot equal to both -1 and +1. So I'm going to go ahead and put that on my number line. We have a -1 and a +1, and neither of these values will be included. So I'm using an open circle. But everything else is okay. These are the only numbers that will not be in my domain. So I would shade every other region. And we can see here that I have 3 shaded areas. That means that for the domain, I am going to have 3 separate parts. This first part here, remember that the left side is -infinity. We're going to start with -infinity to -1. Since I have another section, remember you use the u. This middle section is from -1 to 1. And then this final section would be from 1 to infinity. And this would be my domain. For this final example, we see here that this is a combination. We have both a rational and a radical function. But we have that radical is in the denominator. If you have a radical in the denominator, keep in mind that the radical has to be greater than or equal to 0. However, it's in the denominator, and denominators cannot equal to 0. So in order to accommodate both of these rules, we can take what is inside of the radical and make it just equal to 0, since the denominator cannot also equal 0. So now that I have that inequality, we can go ahead and solve for x. So you can add the 3 to both sides, giving us 2x is greater than 3, and then divide the 2. So now we have x is greater than 3 over 2. We can put that 3 over 2 on our number line. It is not included. X is greater than, so it's everything to the right. So my domain is going to be parentheses 3 over 2 to infinity. Now we're just going to practice that one more time with these other examples. For a, we have a radical function. And remember that with radical functions, the rule is that the inside of the radical cannot be less than 0. So I am going to take that radical, 2x minus 4, and make it greater than or equal to 0. Now I'm going to go ahead and solve for x. So we can add 4 to both sides, and we get that 2x is greater than or equal to 4. Then divide the 2, and we get that x is greater than or equal to 2. Put that on your number line if you choose to do so. We start at 2, go towards infinity, so my domain would be bracket 2 to infinity. For this one here, remember that this is a rational function. And in rational functions, the denominators cannot equal to 0. So we're going to take that x squared plus 7x plus 12, and it cannot equal to 0. It does not matter what the numerator is. It's only the denominator. The denominator cannot equal 0. From here, this is a quadratic trinomial, meaning that in order to solve for this, we have to factor. And remember that factoring involves us opening two parentheses. Since there is nothing in front of the x squared, we would just put x and x. And then we would have to look at what two numbers multiply to give us a positive 12 and add to give us a positive 7, which would be a positive 4 and a positive 3. That means that x squared plus 7x plus 12 is equivalent to x plus 4 times x plus 3. Now that you have it factored, we can make each individual factor not equal to 0. So that way I can solve for those excluded values. For each of these, you would just have to subtract. And we get that x cannot equal to negative 4, as well as x cannot equal to negative 3. These are my excluded values, negative 4 and negative 3. But everything in between is okay. So my domain would be from negative infinity to negative 4, union negative 4 to negative 3, union negative 3 to infinity. And remember that we're not including any of these values because it cannot equal to. For this last one, this is where we have that rational and radical combo. The radical is in the denominator, therefore that 3x plus 9 has to be greater than 0. And then we use this inequality to solve. So I would subtract the 9, and we get 3x is greater than 9, and then divide the 3. And so x is greater than 3. You can put it on your number line. Remember, open circle because it is not included, and it is greater than. Therefore, the domain is parentheses 3 to infinity. And that's finding domain algebraically.